General solution for step and natural responses, RC circuits. So the goals for this slideshow and this video is one is going to be understanding the general solution for step and natural responses of an RC circuit. Number two is we're going to learn how to use it for an RC circuit. And three is going to be using the general solution method to find an RC circuit's natural or step response. And number four is determining whether a problem calls for a step response or a natural response. So for the first slide is we're going to determine how to know if it's going to be a step response or a natural response problem. And so first you want to examine the circuit. And you're going to examine it after the switch. So right now it should be like that, but after switching it'll be like this. So then the circuit of interest is going to be all of this bit right here. And looking at this one by itself, isolated from the left, we see that the circuit is just capacitor and resistors. So there's no independent source in the circuit, so it's a natural response problem. Step response. The step response of an RC circuit describes the behavior of the circuit when a step input voltage or current is applied. And below we have the general formula and a simplified formula. And through these, we see that Vt is the voltage across the capacitor at time t. V final is going to be the final voltage across the capacitor after reaching a steady state. VO is the initial voltage across the capacitor, and T equals RC, or tau, the Greek letter, is the time constant of the circuit. So the applications of step solution is one, we're going to determine the circuit parameters, which is going to be like identifying the R resistance and C capacitance. Two is define the initial and final conditions, so VF, VI. Three, we're going to calculate the time constant. Four, we're going to write the formula. Five, substitute the values that were given. Six, we're going to analyze the response. And seven, we're going to verify and see if it all makes sense. So here's an example problem. We're given an RC circuit with a resistance of 2 kilo ohms and a capacitance of 1 microfarad. The circuit is initially uncharged, so VI equals 0, and then subjected to a step input, charging the capacitor to VF equals 10 volts. So first we're going to start with the equation from last slide. I'm using the simplified one, so VT equals VF times 1 minus e to the power of negative t over RC, or tau. And after that, we're going to substitute with the given values. So instead of V final, we're given 10. So we're going to do VT equals 10 times 1 minus e to the power of negative t. And then instead of RC, we're going to substitute with 2 kilo ohms times 1 microfarad. So we substitute with the given values. And then the third, final step of it is we're going to simplify that down. So VT equals 10 times 1 minus e to the negative t power over 2 ms. All right, and next we have natural response. The natural response of an RC circuit describes the behavior of the circuit when it's subjected to initial conditions. For example, initial charge or voltage, and then left to evolve without any external input. And below we have the formula, Vt equals Vo times E. And the application of natural response, for number one, you want to define it. define the circuit. So you want to look for, again, R resistance and C capacitance. 2, we're going to determine initial conditions like VI. And 3, we're going to calculate time constant. 4, write the formula. 5, substitute. 6, analyze. 7, verify. An example for this would be, suppose we have an RC circuit with a resistance of 2 kilo ohms and a capacitance of 0.5 microfarads. The capacitor is initially charged to VO equals 10 volts. So for the first step, we want to calculate time constant. So T tau equals RC, which is equal to 2 kilo ohms times 0.5 microfarads, which gives us 1 ms. And then we'll apply the formula with substitution of values as well. So the formula, first we could put it down, and then after that we want to substitute the values. So after we substitute values given, we'll have Vt equals 10 times e to the power of negative t over 1 ms.